You and your friend play Mario Kart, but they keep beating you. Enraged, you challenge them to a rematch in a week, claiming that Rainbow Road will determine who the real Mario Kart ruler is. Yet, as they laugh and accept your offer, you realize that there are only 168 hours left until the fateful rematch. Instead of practicing, you decide to take the engineering way out and reprogram the Wii remote to reduce the sensitivity so that there's no chance of survival on the winding road of colorful doom. How do you do this, you wonder? How do you even approach an accelerometer? Well, we're about to find out. First, you have to understand SVD. SVD is a helpful tool that lets you take a big matrix and pull out the most important bits by finding patterns. It factors matrices using their eigenvalues. Using SVD, a matrix A can be rewritten as A equals U sigma V transpose. U is a matrix with values corresponding to the dependent variables. V transpose is a matrix with values corresponding to the independent variable, and sigma is a diagonal matrix of eigenvalues. The eigenvalues are in descending order. Another way to write matrix A is as the sum of the different components of U, sigma, and V. The V and U values correspond with the first sigma value and are the most significant elements of the matrix A. Now that you have a basic understanding of SVD, let's apply that knowledge to accelerometers. Accelerometers sense forces using sensors along different axes. Sometimes they can be inefficient because they are overdetermined. For example, in this diagram, the vector shown can be thought of as a combination of any of the three axes. The axes are not orthogonal, so there are too many ways of expressing the true value of the vector. This is what SVD aims to solve by finding the best axes to represent a vector with, both in direction and magnitude. The closer a vector is to the axis, the better representation it will get from that axis. The same goes for the magnitude of the axes, where the larger the magnitude, the more value will be translated, and therefore the more accurate it will be. The output of accelerometers is a voltage Z. Z equals the gain of a sensor times force plus the bias of a sensor. Because gain and bias are constant for a single sensor, even as force varies, you can arrange all of the different values of Z in a J by I matrix with the different sensors going along the J axis and the different forces going along the I axis. After arranging the matrix, you can subtract the bias so that you are only analyzing the gain of the different sensors and how they will pick up on the force F. Next step, SVD. By arranging the matrix as a sum of different sigma, U, and V transpose values, you can differentiate between which signals are significant and which ones are just noise. The sigma values rank which components of the SVD are the most important. The different U values correspond to which sensors are the most important, and the different V transpose values correspond to the strength of each force. That means that whichever sensor has the highest U value is the best able to capture the magnitude of a force. For example, this matrix has a very important second sensor because that is where the highest U value is. The second force is also the strongest because that is where the highest V transpose value is. Now that you understand how to optimize an accelerometer using SVD, go win some Mario Kart. Just don't ask how to code any of this.